Alright, so today we're continuing our discussion of analytic manifolds, and we're going to start off with morphisms. So we're going to let x and y be analytic manifolds. A function f from x to y is said to be an analytic function, or alternatively a morphism, if, first off, f is continuous, secondly, f is locally given by analytic functions, is how you describe this, which is that there exists atlases, atlases A of x and B of y such that for a chart in a map in our first atlas, and a second chart in our second atlas, we have is V, C, N, and B. Then for W as the intersection of U and the preimage of the open map of our second chart under the morphism, which we know is going to be open by topology, and the composite. So we have phi W we have this, the image of this map in under phi. We're going backwards to get into V. Applying to F. I think this first one is supposed to be W. And then F sends that to V, because every element in W has to be in the preimage of V under F, which we can then send by C to C of V. And this composite has to be analytic. A couple of remarks on this. First off, as previously stated, we describe condition 2 by saying that F is locally given by analytic functions, since in coordinates our composite C acting on F acting on the inverse image of phi may be written as n tuples of analytic functions of m variables. And we also see condition 2 is independent of our choice of atlas on both sides. By the same mechanisms that we use to show that it is an equivalence relation. And we can also note that the composition of morphisms is a morphism the identity map on a morphism on a manifold, is a morphism and finally we can suppose we have a function f from x to y and g from y to x with their composites, their inverses essentially. Their composites giving the expected identity map. And then f is an isomorphism if and only if f and g are morphisms. Now, we're going to look at a theorem. We're not going to prove it, just for the fun of it. I wouldn't call it obvious, but necessarily, but let K be algebraically closed of characteristic 0. And that f from x to y, a morphism of analytic manifolds. If f is a homeomorphism, it is an analytic isomorphism. And that should be fairly easy to see, hopefully. Like, if you could probably convince yourself of this. And remark, this is a counterexample. This is false on, say, K being R, which is not algebraically closed, as we know. For example, taking our function just being cubed. From the reals to the reals. Alright. Next up, we're going to look how to combine manifolds with products and sums. Okay, well, first off, obviously it can be products. we're going to let xi over an indexing set be a finite collection of manifolds and let AI be an atlas for xi for each xi. Suppose we have a chart Ci in each AI, with Ci decomposing into open set UI, function phi, dimension ni. Define the product. We define the product. I forget how to word this. The product as just the component-wise product. The product of the open sets, the product of the maps, and then I guess it's going to be the sum of the dimensions. So this is the topological product of our open sets. And then we're just like producting our maps to work on each such set. Now we set X to be the product of our collection of manifolds, and our atlas to be the collection of the products of our charts. Then X is a topological space with atlas A. And these together are called the product of our xi. We have the universal product, the universal property for products. That is for any manifold Y. The set of morphisms from Y to the product of the xi is the product of the morphisms from Y to our xi. Next we have sums, and sums are disjoint unions. You can let x I be an arbitrary family of manifolds. Let the sum of xi, or alternatively the disjoint union of our xi, denote the disjoint union of the topological spaces xi. Then, as we saw in our last video as an example, there exists a unique manifold structure on the disjoint union of our xi compatible with the manifold structure on each xi. X with this structure is called the sum or disjoint union of our collection of xi for I and I. And we have our universal property for all manifolds Y. The morphisms from the disjoint union of xi to y is the product of the morphisms from each xi to y. And so, Appendix 2, and later on they define the structure of compact manifolds defined over locally compact ultrametric fields. And that's something we'll look at eventually. This next section, I'm a little scared for how long this will take. Hopefully we won't have to split this up. But, oh no, never mind. Next up, we are looking at something which I actually don't know anything about. Germs of analytic functions. Like, all of this up to this point I have seen. Sorry, I kicked my chair. Up to this point I've seen all this before. This is where things start getting a little messy for me. So we're going to let x be a point in our manifold x, and we're going to let underlined f of x be the set of pairs of u phi, where u is an open neighborhood of x and phi is an analytic function on u. And then the set f underscore x is called the set of local functions at x. And we introduce an equivalence relation on f underscore x as follows. We say two elements of f of x, say u and phi and v and psi are equivalent if there exists, if there is an open neighborhood W of X such that W is inside their intersection and restriction of their analytic functions to this intersection is the same. The set of equivalence classes of f bar x is denoted h underline of x and is called the germs of analytic functions at x, or the local, or alternatively the local ring at x. Now we define, for this to be a ring we need addition and multiplication in h underline of x. Let f and g be germs of functions at x. I want to choose a representative, because we're in the set of equivalence classes, right? So we choose a representative pair for f and a representative pair for g. And we set W to be the intersection of their domains, their open sets. Then f plus g is defined to be the class of, W is going to be our domain, and the function is just the sum of these functions on that area. And f times g is defined to be the class. Once again, we're on W, and we're just taking the restrictions and doing pointwise multiplication. So, pretty intuitive. And these are, of course, independent of the choice made. You need to verify that because we're wanting to do this all over the equivalence class, but it's pretty easy to see in this case. There is a canonical map K to a germ of f of x, sending an element alpha in our K to domain x, and then C alpha, with C alpha being the constant function alpha on x. And so the domain in this case is just the whole space, because it's a constant map. You're not going to ever run into any problems with the domain. This map induces a canonical inclusion, which they write as a dotless I, which I'm going to write like that to make it more clear, from K to the equivalence classes of germs, which makes H underline of X a K algebra. And there's also a canonical map from the equivalence class of germs on of X to K, which is the evaluation map. So RU comma phi in the equivalence class of germs is going to just be evaluated at X, which is going to induce a canonical homomorphism theta from H bar X to K of H bar X onto K. Then for F in H bar X, we let F of X denote theta of F, and we call F of X the value of F at X. The kernel M of X of functions, local function at X which take a value of 0 on X. This kernel of, it's the kernel of theta I should say, is a maximal ideal. And looking at this, I'm pretty sure if you divide external line X by this kernel, you're going to recover the base field, I believe. Because with that division, you're essentially evaluating the map to be the value at 0 is what you're left with. Alright, anyways. Since theta is a left inverse of our other canonical map, it's the identity on ring. Yeah, oh, look at that. I didn't even read ahead. There's a canonical decomposition of the equivalence class at H of germs at X into essentially the value that that function takes at identity, and plus a local function which takes 0 at X. We will identify K with this IK, so yeah, it's just like, essentially, if you think of our functions M of X as a power series, I believe, this is just splitting off the term of order 0, essentially. And now we're going to show that h under bar of x is a local ring by means of the following stronger statement. This is a lemma. Let U phi n be a chart of x. And phi induces review composition and isomorphism. Let's do it on a new line. Isomorphism phi bar from h underline 0 to h underline x such that phi bar of the kernel of theta at 0 is the kernel of theta at x. And yeah, they're going to say h line 0 is the ring of germs of functions at 0 in k to the n with maximal ideal m0. That's all obviously just substituting 0 into our notation. And here, and we have that h underline 0 is isomorphic to the local ring of convergent power series in n variables. And proof, everything here is pre-automatic except for saying that the ring of convergent power series in variables is local. So to show that, we're going to show if f is a convergent power series such that f of 0 is non-zero, then f is invertible. And we're going to assume, once again, without loss of generality, we're going to have f be 1 plus theta with c 0 being 0. I don't know why I see a Greek letter and just list a random letter, even though I know what it is. Since gx as being 1 over x is analytic near 1, not at 0 of course, 1 over f being the composite of g and f is analytic near 0. Suppose f is from our equivalent class of germs of functions of analytic functions at x, and f is non-zero. We define ord x of f as the least integer mu such that f is not a mu plus 1 power of an element in the kernel of theta at x. Then for any chart u phi n, the order x of f is the least integer mu such that phi bar of f has in its power series expansion a non-vanishing homogeneous term of total degree mu. Okay, maybe we're a little under time, but our next chapter, yeah, I think it's going to be a bit too much. I mean, let's see, we've done, how much have we done? We've done 1 page, 2, yeah, that's going to like double our time. So I guess we'll call it here with a bit of a shorter episode today. Sorry about that for our first one, but next time hopefully we should be yeah, we'll be getting into like tangent and cotangent spaces and maybe the inverse function theorem, so look forward to that.